Ladies and gentlemen, welcome to the Royal Society. That's to all of you gathered in this room and to the audience in the overflow room behind. A very warm welcome. My name's David Reed. I'm a Vice President and the Biological Secretary of the Royal Society, and I'm taking charge of proceedings this evening. My first task is to ask you that if you have brought a mobile phone into the room, and we have evidence that at least one person has, could you ensure that it's actually switched off now? Thank you. In the finest traditions of many of the founding pioneers of the Royal Society, our speaker tonight, Professor James Lovelock, is a true polymath. He has variously been recognized, indeed honored, as an inventor, an engineer, a chemist, a geologist, and an ecologist, amongst other things. However, most remarkably, and perhaps remarkably in his own time, he has shown the ability to integrate his expertise in all of these individual disciplines, and he's done this so effectively that he's been able to demonstrate the extent to which our planet operates as a self-regulating system. What James first proposed as the Gaia Hypothesis way back in 1968 has evolved to form the basis of what we now routinely refer to as Earth system science. This concept provides us with the essential interdisciplinary basis from which to investigate our planet, and most importantly, to begin to understand the impacts of humans upon it. James started his career in the early 1950s in medicine, where he determined the nature of freezing damage to mammalian tissues and demonstrated mechanisms for its alleviation. Using his prolific skills as an inventor, he developed early on, and around the same time, an electron capture device, or ECD. And using it in a chromatographic context, he began to demonstrate the ubiquitous distribution of polychlorinated biphenyls, PCBs, as pesticide residues in the terrestrial environment, notably in soils. He later went on to demonstrate the widespread occurrence of other halogen-bearing molecules, most notably the chlorofluorophenols, CFCs, in the atmosphere. He subsequently was able to show that these chemicals, by threatening the ozone layer, posed a direct threat to the equilibrium of the atmosphere enveloping the Earth. The earliest of James' discoveries were much publicized at their time by the writings of people like Rachel Carson, particularly in Silent Spring. And they were of such significance that they are now seen to have been involved and to have played a key role in the initiation of what we recognize as the global environment movement. James has received numerous awards and honors, amongst which, to mention but a few, are the first Amsterdam Prize for the Environment, awarded by the Royal Netherlands Academy of Arts and Sciences in 1990, the Volvo Prize for the Environment in 1996, and the Blue Planet Prize in 1997. The Wollaston Medal of the Geological Society followed in 2006, as did the John Collier Medal from the Institute of Chemical Engineers. These awards, amongst other things, demonstrate the huge diversity of the contributions that James has made to so many areas of science. He was elected a Fellow of the Royal Society in 1974 and was awarded a CBE in 1990. In 2003, Professor Lovelock was made a Companion of Honor by Her Majesty the Queen. Ladies and gentlemen, it gives me great pleasure to ask Professor James Lovelock to present his lecture entitled Climate Change on the Living Earth. James.
Thank you, Sir David, for that most gracious introduction. You've certainly given me something to speak up to. Ladies and gentlemen, most of you by now will be aware of the main conclusions of the highly respected Intergovernmental Panel on Climate Change's 2007 report. And I'm sure that we are all of us proud that they were awarded this year's Nobel Peace Prize, along with Al Gore. The report itself speaks of the real possibility of severe climate change, but it is written in properly cautious scientific language and gives the impression that global heating is serious, but the worst consequences might be avoidable, particularly if we take appropriate action now. Inevitably, the conclusion of the report needs constant revision in the light of real climate change. Sadly, even the most pessimistic of the climate prophets who form the IPCC panel do not appear to have noticed how rapidly the climate is in fact changing. My first intimation that we might be on the brink of disaster came in May 2004, when my wife Sandy and I visited the United Kingdom's primary climate research centre, the Hadley Centre at Exeter. It's a place of excellence and an important part of the IPCC. And while we were there, we talked with a range of scientists. Some were concerned with the melting of the ice floating in the Arctic, others with Greenland's vanishing glaciers and glaciers vanishing elsewhere in the world. And later in the day, we heard from Peter Cox and Richard Betts, two of the lead scientists at the Hadley Centre, about the way that the great tropical and boreal forests are not only vanishing, just like the ice, but also changing as the world grows hotter. And then we talked of our own concern about the way that the ocean life was disappearing as the surface waters warmed and stratified. The climate scientists with whom we talked spoke of their observations and models of global heating in the regions that each of them were investigating. Taken separately, each of these regional investigations presented convincing evidence of positive feedback and accelerating change. They told of their research in detail, but in that detached and properly scientific manner we expect from all of us scientists. But it sounded to both of us almost as if they were describing some other planet, not the Earth. This was in itself disturbing, but much more so was the fact that those concerned, for example, with the melting of polar ice, although well aware of their colleagues working on the similar vanishing of the tropical forest, seemed to present their own research as something separate from the heating of the whole planet. There was also a tendency to present the whole Earth system as if it was no more than the simple addition of its parts, something I knew is rarely ever true of a dynamic system. Sandy and I left with a deep sense that what we'd heard was truly serious, and the visit profoundly changed my views of the future. In defense of my friends at the Hadley Centre, I have to say that almost everyone concerned with climate change in 2004, and that included me before the visit, had this same detached approach to climate research. We were worried, but there was no sense of pressing urgency. And I must add that this was all we perceived was the correct and objective way to think about it. When I looked at the IPCC report again, it was with a new sense of awareness. I now saw it as the scariest official document I'd ever read. It was all too clear that the message from the climate scientists was not reaching the public, and especially not in the United States. I'm talking, of course, about 2004. This, of course, was before Al Gore presented his book and film. I now take an apocalyptic view of the future because I see the 6 to 8 billions of humans faced with ever-diminishing supplies of food and water in an increasingly intolerable climate. You may well ask How have we scientists let this potentially disastrous future steal up on us unaware? There are several reasons. Among them is our success at solving the important but more manageable problem of stratospheric ozone depletion. This employed nearly all of the lead atmospheric scientists at the time, and I suspect that it gave us all a false confidence in our ability to deal with the far greater and much more complex danger of global heating. Another reason for the slow recognition of the threat of adverse climate change is the division of science itself into almost unconnected specialties. If you look back at the writings of Earth scientists just 30 or 40 years ago, you will find them confident that the composition and climate of our planet were completely explicable from chemistry and physics, and that life was just a passenger. Life scientists of the same time period were equally confident that organisms evolved according to Darwin's great vision and adapted to the Earth that was fully described by their Earth science colleagues in the buildings across the campus. This was a harmful and irrational division of science, and I'm glad to say it's slowly fading, but it still persists and has led to the deplorable separation of the assessment of global change between two different international bodies, one based on physical science, the IPCC, and the other on biology, the Millennium Ecology Assessment Commission. The Earth is not so divided, and so long as we treat it as two separate entities, the geosphere for the material Earth and the biosphere for life, I fear we will fail to understand our planet. 42 years ago, I was working at NASA's Jet Propulsion Laboratory in California and was given the wonderful opportunity to see at first hand evidence about the nature of our sister planets, Mars and Venus. They were quite obviously dead planets and quite different from our lush and lively world, almost as different as is one of us from a stone statue. The Earth has an atmosphere that is wholly unstable in a thermodynamic sense. Gases such as oxygen and methane are massively produced, yet coexist in stable dynamic equilibrium. So, as Sir David said, I introduced the hypothesis that life at the surface of the Earth regulates the composition and chemistry of our atmosphere so as always to keep it habitable. And my friend, the Nobel Prize-winning novelist William Golding, suggested that I call the hypothesis Gaia. In some ways, I wish he hadn't, because it's caused a hell of a lot of trouble since. Later, during the 1970s, I developed the idea further in collaboration with that eminent biologist, Lynn Margulis. But we soon discovered that what we called the Gaia hypothesis was far from popular in science. Biologists were particularly outspoken, and in the 1970s, they rubbished the infant hypothesis in the mistaken belief that it was like creationism, contrary to the evolution by natural selection. The demolition was so effective that even today, few scientists are happy with the word Gaia, and many still see it as a New Age fantasy. I went on to refute their criticism with evidence of self-regulation gathered from the Earth itself, and by mathematical models that illustrated how planetary self-regulation could in fact take place. And nowadays, Gaia theory, worked on by a number of us, including my colleague Tim Lenton in the audience, is a top-down physiologist's view of the Earth system and sees the Earth as a dynamic, responsive planet and explains why it's so different from Mars and Venus. Now, in different times, much earlier than this, these arguments would merely have been part of the natural history of science. Sadly, now they seriously interfere with the evolution of a proper understanding of the Earth system when we badly need it. We need it to understand the consequences of adding greenhouse gases to the air, and equally the consequences of removing natural forests for farmlands, because each of these acts disables the Earth system's capacity to regulate itself. Most of the large climate models used to predict future climate still rely mainly on atmospheric physics, and this includes the models on which the IPCC report is based. The influence of the clouds and of the ocean are only incompletely included, and that of the biota hardly at all. Present-day climate models are good at explaining past climates, but seem unable to agree on the course of global heating beyond about mid-century. By the end of the century, predictions vary over a wide range, but then who sensibly would try to predict that far ahead? This stark view was reinforced in May this year by the publication by Ramsdorff and his colleagues of high-quality measurements of the rise in global mean temperature, sea level, and carbon dioxide. And these show that even the gloomiest predictions of the IPCC were either at or underestimating the severity of climate change. Can I have the first slide, please? Yes. This is taken from the Ramsdorff paper, and it shows just two of the panels. The lower one is the sea level change in centimeters over time. And you can see the solid line here represents the actual change. And here is the band of predictions from the IPCC report. You can see the extent to which there is a gap here. There's a serious gap approaching twice as fast a rate of melting as the panel predicted. And then when you look at temperature, again, the wobbling red and blue lines indicate measurements of global temperature, whereas the band is the IPCC report. And you can see the actual temperatures are wobbling very close to and occasionally above the gloomiest of the IPCC predictions. Can I have the next slide, please? Now, this is a much more recent one, and it shows the melting of the floating ice in the North Polar region. And were this a business report showing sales and profits, the downfall here will cause anxiety amongst the shareholders and the board. But this is our planet that we're looking at. And if you extrapolate the rate of fall, which some have done, it would suggest that in as little a time as 5 years, there will be precious little ice left floating in the North Polar Basin. If you just take the average, it shows that all is likely to be gone in 10 or 20 years. Now, this compares with the earlier IPCC predictions, who said it might be gone by 2100. It's a huge change, and it's happening. And what is important about this is, of course, that when that white reflecting ice changes to dark sea, the added heat load to the Earth from the absorption of summer sunlight, not only up here, but also in the Southern Ocean, will be a quantity comparable with the heating caused by all of the carbon dioxide added to the air so far. If there's any point I wish to make tonight, it is that the Earth is joining our act of global heating, and with increasing enthusiasm. In 2001, there was a serious attempt to bring Earth and life sciences together. At a major scientific meeting in Amsterdam in the Netherlands, over 1,000 Earth and life scientists signed a declaration that had as its first point, the Earth system is a self-regulating system comprising all life, including humans, the atmosphere, ocean, and surface rocks. My friends who were at this meeting wrote to tell me that Gaia was now endorsed in science. But in science, as in human affairs, the perceived conventional wisdom does not change easily or quickly. At Amsterdam, scientists acknowledged Earth system science, but continued to work separately as before. One day they said, we will unite as a single science, but not yet. It's easy to see why scientists are so reluctant to abandon their familiar and comfortable paths. Darwinian biology, in the hands of the distinguished fellows of this society, William Hamilton, John Maynard Smith, and our past president, Lord May, has been a wonderfully rich and productive branch of science. And by great good fortune, they had that most eloquent fellow, also an author, Richard Dawkins, to put forward their thoughts before the public and other scientists. But just as Newtonian physics was found incomplete at the particle and cosmic scales, so I think Darwinism is incomplete when it tries to explain the world beyond the phenotype. In particular, it fails to see that organisms do more than adapt to a dead, fixed world. They are naturally selected in a world that was changed by their ancestors, and in turn, their interaction with the material environment sets the scene for the next round of evolution. The air, the ocean, and the surface rocks are all either direct products of life or else have been massively altered by its presence. Our difficulty in understanding the Earth can, I think, usefully be compared with that of understanding economics. The 18th century economist Adam Smith is respected for his intuition of an invisible guiding hand that makes rampant commercial self-interest somehow work for the common good. 200 years later, we face a similar paradox. We know that the Earth is a benign and comfortable place for life, and has been for most of its history. So how have selfish genes allowed the evolution of so altruistic a planet? It's easy to see now how fit organisms are naturally selected, but how can the common good for all life also come through natural selection? William Hamilton said, I think we need a Newton to solve this problem. But I wonder if we have discovered that as the Earth system matures, it keeps its climate and chemistry always fit for life, and the invisible hand that does the regulation is feedback between its living and non-living parts. But this knowledge has only just entered the domain of science and is not yet conventional wisdom. It took a long time before we recognized that feedback between social and market forces cannot be ignored. So I suspect that we face a similar slow learning process about our relationships with the Earth. Meanwhile, we are still trying to shape it to our own ends and needs, and we ignore, even disable, its own powerful guiding hand. In our hubris, we believe that we can be stewards of the Earth long before we understand it. Perhaps science and economics have more in common than we used to think. A few weeks ago, the distinguished economist P. Dasgupta compared the complexity and nonlinearity of economic systems with those of climate systems. The long-term history of the Earth suggests the existence of hot and cold stable states, what the geologists often refer to as the greenhouses and the ice houses. The best-known hothouse occurred 55 million years ago at the beginning of the Eocene period. In that event, between 1 and 2 teratons of carbon dioxide were released into the air by a geological accident. We are fairly sure about this from measurements made by Professor Elderfield of Cambridge University and his colleagues, and from the researchers of Henrik Svensson and colleagues at Oslo University. Putting this much carbon dioxide in the air caused the temperatures of the Arctic and temperate regions to rise about 8 degrees Celsius and the tropics 5 degrees. And it took about 200,000 years for conditions to return to their previous state. In the 20th century, we injected about half that much CO2, and we and the Earth itself now look soon likely to release more than a teraton of CO2. Global heating 55 million years ago took place much more slowly than now. The injection of gaseous carbon compounds into the atmosphere may have taken place over a period as long as 10,000 years, instead of about 200 as we are now doing. The great rapidity with which we are adding carbon gases to the air is as damaging in some ways as the quantity. The rapidity of the pollution gives the Earth system little time to adjust, and this is particularly important for ocean ecosystems. The rapid accumulation of carbon dioxide in the surface water is making them too acid for shell-forming organisms. This did not appear to happen during the Eocene event because there was time then for the mixing in of the more alkaline, deeper waters to neutralize the surface ocean. There are other differences, of course, between the Earth 55 million years ago and now. The sun was 0.5% cooler, and there's no agriculture anywhere, so that natural vegetation was free to regulate the climate. Another difference was that the world then was not experiencing that strange phenomena, global dimming, the 2 to 3 degrees of global cooling caused by the atmospheric aerosol from man-made pollution. The haze from it covers most of the northern hemisphere and offsets global heating by reflecting sunlight, and more importantly, by nucleating clouds that reflect even more sunlight. The aerosol particles of the haze persist in the air for only a few weeks, whereas carbon dioxide persists for 50 to 100 years, so that any economic downturn or planned cutback in fossil fuel use, which lessened the aerosol density, would intensify the heating. And if there were a 100% cut in fossil fuel combustion, it might get considerably hotter, not cooler. And this is why I sometimes say I think we live in a fool's climate. We're damned if we continue to burn fuel and damned if we stop too suddenly. It is not difficult to make a simple numerical model of a live Earth with an ocean and land biota taking an active part in climate regulation, and then try the experiment of adding a teraton of carbon dioxide to the model to mimic what we are doing. I did this in collaboration with the geochemist Lee Kump, and we published it as long ago as 1994 in Nature. Can I have the next slide, please? Yes, this is this simple model. The upper panel shows you temperature change as the carbon dioxide goes into the atmosphere, starting off at something not far from what we have now. The very uppermost panel is the temperature variations on a dead Earth with no life on it, a much hotter place. And the little wobbles are just seasonal and annual variations in the input of solar heat. They're very useful in the model in that they diagnose the presence of positive feedback. Where the amplitude of the fluctuations is greater, then we have positive feedback. Where it's lower, negative feedback. Now, the interesting thing about this model, where it differs in two ways from the IPCC models, is that it suggests everything goes along and is regulated reasonably well, apart from the fluctuations, until suddenly there's a jump in temperature to a new stable state, which is well regulated. The IPCC, if you look at it, seems to suggest temperature just rises steadily with increasing CO2, and, more seriously, suggests that if you cut back emissions, it would go back down again. This model, unfortunately, suggests that once you get up to this region, or even a high on the slope, cutting back CO2 right down to pre-industrial levels makes very little difference to the temperature. The system has committed itself to the change. You may ask, why should we take a simple model like this seriously when so many of the world's climate scientists are in agreement with the IPCC predictions? First, although simple, it is a model of the whole Earth system and not merely one based almost entirely on atmospheric physics. Perhaps the most important message from this simple model is its implication that ocean ecosystems dominate the cooler period of the Earth's history. You can see the growth of algae here fluctuating. And land plants dominate the hot period, the greenhouse. Some indication that this might be true comes from papers appearing just this very week from Andrew Watson and Corinne Leclerc, both of whom show measurements in the ocean indicating a decline in the ability of the ocean system to take in CO2, and occurring in the last few years. What I've said so far seems to imply that there's little we can do to prevent the Earth system moving to one of these hot, stable states. But in no way do I mean that there is no hope for us and there's nothing we can do. I much more see our predicament as like that faced by a nation that is about to be invaded by a powerful enemy. We're now at war with the Earth, and as in a blitzkrieg, events proceed faster than we can respond to them. We're in the strange position of living on a planet where climate and compositional change, that's to say geological change, is now so rapid that it is happening too fast for us to react to it. And I think if you think back to that changes in the floating ice, that shows you just how fast change can occur. For this reason alone, I think it's probably too late for sustainable development. Enlightened living of that kind might have worked 200 years ago in Malthus's time, but not now. The positive feedback on the heating of the melting of the floating ice in Arctic and Antarctic regions, as I mentioned, is equivalent or nearly equivalent to the heat from all of the pollution we have so far added. And this suggests that implementing Kyoto or some super Kyoto is unlikely to succeed. Geoengineering schemes will certainly be tried, especially in America, which is a can-do nation, and that these include sunshades in space, such as described by Lower Woods, stratospheric aerosols to reflect sunlight. A number of quite distinguished scientists have been involved with that one. I think it was first suggested in the 1970s by the Russian scientist Badiko, a considerable figure in atmospheric science. It was followed up by Robert Dickinson in Arizona a few years later, and most recently by Paul Crutzen in Germany and by Ken Caldeira in the United States. And then there is, of course, the artificial generation of marine stratus clouds just above the ocean, which Latham of NCAR has suggested. All of these have the potential temporarily to halt global heating and could be part of a comprehensive treatment. I know that the environmental movement does not like and has almost a gut reaction to technological fixes, but I don't think these should be condemned without considering their value as something that extends the time that we have to act. In the longer run, I agree with the environmentalists. They're probably no more a cure than is dialysis for kidney failure for one of us. But then, who would refuse dialysis if death was the alternative? There is a third approach that is less invasive, and it is to think of the Earth as a live, self-regulating system and devise ways to alter the sign of the feedback from one or more of the 5 main climate-regulating processes, from positive to negative. The first signs of this kind of thinking came from the charity Cool Earth, that proposed, quite simply, using its funds to pay indigenous people to protect their natural forest ecosystems as something much better than paying money to plant trees. You can't plant an ecosystem. It takes an incredible time for one to form. Another example would be the direct synthesis of food from carbon dioxide, nitrogen, and water taken from the environment. Now, this would have two advantages. One, it would reduce the amount of land being used for farming. And secondly, of course, it would be a great way of sequestering carbon dioxide from the atmosphere. And there is a third approach that Chris Rapley and I raised a few weeks ago in the journal Nature. And that was the possibility of using ocean ecosystems, which are 70% of the Earth's surface, using them to turn them from positive to negative feedback on heating by mixing cool, nutrient-rich subsurface waters with a stable but barren floating top layer of the ocean. This, we thought, would feed algal growth and make the surface a more efficient sink for carbon dioxide. And algal growth would, of course, also release dimethyl sulfide gas, which is a precursor of clouds. This could be achieved by a relatively simple system of pipes and would be driven automatically by wave energy. Small-scale attempts to do this have been described and appear to work. We are well aware that there could be practical reasons why this simple idea might not work, such as that the waters of the deeper ocean are richer in CO2 than the surface, and to bring them up would add to the burden of carbon dioxide in the atmosphere. But we still think that the idea is worth trying experimentally rather than condemning on model calculations. We raise the idea to show the value of thinking of the Earth as a living system whose gigantic stores of energy might be available for use in its and our interest. We hope that our idea might stimulate other proposals of this kind, and among them would be one that might do the job. We also wanted to show that a Gaian approach to stimulating the Earth to cure itself was more than mere rhetoric. Perhaps our first task is to stop thinking blindly that by reducing our carbon footprint, we are doing enough. We have to understand that by abrading the skin of the planet to provide farmland, we have already destroyed 40% of the Earth's natural ecosystems, and these were what previously served to sustain a stable climate. If we go on and take out the remainder for biofuels, we really will be in trouble. Most of all, we have to understand that the Earth system is now in positive feedback and is moving ineluctably towards the stable state of one of the past hot climates. I can't stress too strongly the dangers inherent in systems in positive feedback. Imagine that you're living in a wooden house and that you built so large a fire to warm yourself in the cold of winter that the furniture near the fire begins smouldering. If you don't get out soon, positive feedback will ensure that the whole house is consumed by fire in minutes. Few seem to realize that the present IPCC models predict almost unanimously that by 2040, the average summer of Europe will be as hot as the summer of 2003, when over 30,000 died from heat. By then, of course, we may cool ourselves with air conditioning and learn to live in a climate that is no worse than that of Baghdad now, without the war. But without extensive irrigation, the plants will die, and both farming and natural ecosystems will be replaced by scrub and desert. What will there be to eat? And the same dire changes will affect much of the rest of the world. I can envisage the Americans migrating into Canada. The Chinese, where will they go? Siberia, perhaps, or possibly Africa. When we were hunter-gatherers, and only a few million of us occupied the Earth, we were in balance with nature, and the carbon dioxide we breathed out was absorbed by the plants in its entirety. Now the air we breathe, the 6+ billions of us, puts in 2 gigatons of carbon dioxide every year, and that's 4 times the total of the airlines of the world. And the agribusiness food plants do not keep it in balance in the way that the natural ecosystems once did. We face a stark choice now between a return to a natural life as a small band of hunter-gatherers or a much reduced high-tech civilization also in balance with nature. Paul and Anne Ehrlich were right to say, as long ago as 1980, that it was preposterous to imagine as possible a population of 6 billions living a first-world lifestyle. Because it might help slow the pace of global heating, we have to do, of course, our best to reduce emission and to lessen our destruction of natural forests to feed and house ourselves. But this is unlikely to be enough, and we will have to learn to adapt to the changes that will soon take place. During the early Eocene global heating, there was no great extinction, and this may have been because life had time to migrate to the cooler regions of the Arctic and Antarctic and remain there until the planet cooled again. So this may happen again, and humans, animals, and plants are already migrating. Scandinavia and the oceanic parts of northern Europe, such as the British Isles, may be spared the worst of the heat and drought that global heating brings. But this puts on us the special responsibility to stay civilized and give refuge to an unimaginably large influx of climate refugees. Perhaps we must steer a path between the counsel to perfection of Gro Brundtland's concept of sustainable development and the alternative counsel to perfection of the deep ecologist's idea of a return to living a life balanced with the Earth system. This middle way was touched on by our President Lord Rees in his book, The Final Century, but it will require difficult choices on what technologies to abandon and what to retain. I think we should look upon our path as a sustainable retreat. And my friend Sir Crispin Tickell says, we need a climate catastrophe soon, recognized as such by everyone, and strong, effective leadership. Perhaps the saddest thing is that if we fail, Gaia will lose as much or more than we do. Not only will wildlife and whole ecosystems go extinct, but in human civilization, our planet has a precious resource. We're not merely a disease. We are, through our intelligence and communication, the planetary equivalent of a nervous system. And never forget, we are part of the system, just another species. But we should be the heart and mind of the Earth, not a malady. And so perhaps the greatest value of the Gaia concept lies in its metaphor of a living Earth that reminds us that we're part of it, and that our contract with Gaia is not about human rights alone. It includes human obligations. Thank you.
Take a few questions. James, we'll take a few questions. We regulate questions because, as you may realize, this is a live webcast event, so we require you to have a microphone before you ask your question, and please to stand up while you're giving it. So are there people, can we have a microphone here, and then one at the back, and if you just don't mind, hold on 1 minute while that person gets his microphone. Right, fine, thank you.
Jim, for the benefit of people here, Bob Spicer from the Open University. I agree with you absolutely about the conservative nature of the IPCC. But then, of course, I come at the issue of climate change from a perspective of deep time and previous greenhouse worlds. So I agree absolutely with everything that you said on that score. But one of the problems that has arisen recently is, and this was conveyed to me by a colleague who lives in New Zealand, that Australian politicians, when faced with questions about recent droughts there, started to shift the blame, as it were, and said, well, you know, if this is to do with global warming, it's the scientists' fault for not shouting loudly enough, early enough, so that we could take avoiding action. Now, with the IPCC being sort of conservative, do you see any future for actually getting this message across to those who do not wish to hear?
Thank you, Bob, for that very taxing question. I think, and I agree with Sir Crispin Tickell, that we need a wake-up in the form of a climate event of sufficient severity to make us all realize the whole damn thing is real. And then it will be, my hope is it will be treated like a wartime situation where the whole of all the nations pull together and start reacting effectively. And, but as Sir Crispin said, you need leadership as well. And I'm not too sure the Australian politicians are really fulfilling that role.
Thank you. We'll try and keep the questions and the responses as short as possible so as to get a number of people in. Just before you start, is there another question here? Could we get the microphone to that person at the back? Yes.
Henry Musk, climate change consultant. James, it's good to hear your lecture today. Normally, when I hear you speak, you're very much waving the nuclear baton or flag, and we haven't touched on that, and I'm not going to raise it at the moment. I'm sure it will come up. It seems apparent that what we need to do is decarbonise the grid, and we also need to address transport. It was quite worrying to hear that if we do address transport and it became carbon-free, there'll be a 2 to 3 degree rise in carbon emissions because of a dimming effect gone. Do you feel that concentrated solar power stations in arid zones, bearing in mind there are arid zones on all of the major continents, linked to the generation of hydrogen fuel cell technology to tackle transport, offers at least a respite or a way of extending our time on this fragile Earth?
I wish I did. Unfortunately, I don't think we have time for any such notions. One tends to forget that any major engineering operation takes about 40 years from inception to becoming available in every home. And if you look back, you'll find this is true of nearly all the things we now take for granted. Some of them are a little faster, some are a little slower, but it's that order. And that would apply to power systems. The only ones we can use in time are the ones that are now available.
Sorry, it's a proven technology in the States, and it just needs to link up to the grid. So the infrastructure's there, and also the technology is 25 years old.
You were talking about a global solution. It's no use answering the problem just in a given country.
Thank you. Just before you start, is there another question here? Yes, this lady here. Could you take the microphone there? And there. Yes, you sir, at the back.
Hi, Olive Heffernan from Nature.
Could you hang on? Sorry, you're second. Sorry, it's confusing, but there we are. Right.
Here is Mr. Albarkali from Frozen Isthmus Protection Campaign of the Arctic and North Atlantic Oceans. And it is our view that because of the open space that has opened in the Arctic Ocean, this ice mobility will mean that this ice flips and flops between the melted area and the frozen areas, and therefore the ice will just disappear within few years. What is your view of if we lose the ice by year 2009? Because our expectation that next year this Arctic sea ice crescent, which is the remainder of the polar ice, will escape from the behind of Greenland and Canada, and it will just go to the Russian side, and then it will break into 3 components. And these 3 mini ice caps will be floating all over the place and breaking up into small fragments. So what is your concern and feedback on this methane clathrates and methane on the far Arctic if we lose now the Arctic Ocean sea ice? Our estimate is 2009.
There's the loss of ice and then the impact on methane clathrates.
Right. No, that is a very important question. The melting of floating ice in the Arctic, and perhaps to a lesser extent, although Chris Rapley, who's in the audience, would know more than me, the Antarctic, is rather difficult to predict, because the positive feedback, as that slide I showed you shows, is very great indeed, and it's not wise to make predictions about a system like that, except to say that it looks as if it will crash altogether quite quickly. Whether it's by 2009 or by 2020, I don't know, but it doesn't make very much difference. It's very fast in Earth terms.
Thank you. Now, just before your question, is there... Yes, this gentleman here was next. Right, your turn at last. Thank you.
Hi, Olive Heffernan from Nature. Just in relation to your recent proposal in Nature with Chris Rapley for a geoengineering scheme to pump water from depth to the surface waters, I'm just wondering, you mentioned that there were some concerns about whether it would be scientifically feasible, but do you know whether it would be feasible from an engineering perspective? Is there any idea about that? And also, if it was operational, do you know how much time it would buy us?
Whew, that's tricky. There is an American group called Atmotion, I think, who already are trying out a scheme of that kind, and I think the Japanese also have been interested in it. But I think the main motivation there was to improve fishing rather than to improve the atmosphere. Well, it doesn't really matter. The engineering take I get is that it's well worth a try, and this is all we were asking. There's too much tendency to model the situation in a basement somewhere rather than going out in the ocean and doing some measurements and trying it. And I think the issue is so important, so vital to all of us. You don't ignore any chancy possibility like that, and it would not be very expensive.
Another question there just before. Yes? Could you take the microphone there? Yes, you, sir. No. Right. No, sorry. It's this side first.
Pierre-René Bocquis from French Petroleum Institute. First, a small question. You mentioned the massive release of CO2 55 million years ago, and the date for transition from Cretaceous to Tertiary is 65. So is it 55? Is it a separate event, or is it the transition from Cretaceous to Tertiary? So it's a very small question. And second observation, much more fundamental. What you said today, which is new for probably a large number of us, is that even if we were stopping the use of fossil fuel, let's say most likely through nuclear, because there is no other avenue ready, and we have no alternative to that one. You said we would have a temporary increase by 2 or 3 degrees because we lose the aerosol. But wouldn't it be worse? Because one phenomenon is just accumulating the CO2. The other one is the temporary thing. We'll have to have this little jump. So shouldn't we push for the decarbonization even with this aerosol problem? That's the second question.
Thank you very much. I'll try and answer the second one first. The problem here is, if there's a sudden 2 or 3 degrees Celsius rise in global temperatures, then many parts of the Earth system will begin releasing carbon dioxide to the atmosphere at a very much faster rate than it's doing at the moment. You have to bear in mind that the positive feedback inherent in the system it works its effect regardless of the cause of the temperature rise, whether we do it or whether it does it itself spontaneously. And this is why I feel so strongly there isn't an awful lot we can do in the way of cutting back emissions in time. It's always a matter of in time. Everything is happening exceedingly quickly. And human inertia is huge. I mean, consider, it's over 10 years now since Kyoto. What's happened? We don't react fast enough. Politics isn't fast enough. And that's why I feel that our main effort should go towards adaptation. That we can do. Now, the first question was, can you remind me? Because the 55 million. Oh, yes. That's right. Now, what they call the early Eocene thermal event, 55 million years ago, was a very well clear-cut event. There's lots of evidence, and it's an example of an event where isotopic analysis is particularly useful. We know pretty accurately just how much carbon was put into the atmosphere, and we know how much the temperature rose in various parts from the carbon and oxygen isotopes, respectively. And it's a very sharp, clear-cut event. I don't think there's too much doubt about it, and that's why I chose to mention it. There are earlier events, might have been similar, but the evidence is nowhere near so available.
Good. Just before the question, is there anyone here? You've already got the microphone. The person over here was the next to ask. And then you come next. Yes.
With regard to the positive feedback effect, can we draw any parallels with the possible effect in the planet Venus many millions of years ago, when the positive greenhouse effect took place and possibly destroyed the oceans on that planet, which is very similar size to our own?
I think you're absolutely right. But you have to remember, of course, Venus gets, I think it's about 40% more solar heating than we do. So it went through a period which we are now approaching a lot earlier than we did. One should remember, too, that the Earth system in many ways should be looked on as a rather aged one. I always like to think of it as about the same age as I am, in its 80s, because it's existed for 3.6, possibly 4 billion years, but it looks very much as if it only has about 500 million to go further. By then, the sun gets too hot and those conditions get too Venus-like for comfort.
Now then, where is the microphone at the moment? You've got the microphone. Can we get the microphone to somebody else on? There's one right at the back with the green piece of paper. So you, sir, now.
Jim, Could I just emphasize what you were saying about the suddenness of change? In the relatively recent geological record, around about 11,600 years ago, the change then was very, very quick indeed. The major part of the change took place within about 20 years that took us out of near glaciation into essentially modern climate. Around about 8,200 years ago, again, a sort of 100-year blip that pushed the whole northern hemisphere down very sharply. These changes are almost like gear changes in a car. And models like work like the Stern report, for instance, which is superb, seem to take as sort of assumed some sort of linear change. It might be fast, it might be slow, but it's not sudden. All the record tells us it's sudden. It happens bang. The second comment was that I'm Zimbabwean, and I get daily reports from Bulawayo, where I used to live, of people starving. Just over the border, there's a massive obesity problem. And I'm very pessimistic of our ability to help our neighbours.
Well, thank you, Ewan, for your support, is all I can say. I agree with all you say.
Yes. Somebody's got the microphone, then you, and then a microphone here, please.
Yeah, you were saying that we'd need some sort of ecological disaster to get people's attention. Given the collapse of a massive ice shelf from Canada and the fact that for the first time in recorded history the Northwest Passage is now open, how much more is it going to take?
I think probably the factor that affects people most is a change in their personal incomes. We got a small bit of a one from Hurricane Katrina, which was a pretty disastrous event locally and possibly caused by global heating. The price of fuel suddenly rose sharply, but it wasn't enough. I mean, it needs something that makes people really wince at the rise of cost of living. And that could easily happen as a result of some event, I know not what. Mere deaths, sadly, do not seem to bother people. One's only to think of the European heat wave in 2003. 30,000 is a large number of deaths to occur. And nothing stirred about it except articles in the newspapers about wasn't it wicked of young people to leave their old people to fry to death in flats and things like that, rather than this is what's happening to the Earth.
David Waterlow from DEFRA. It's been a very interesting lecture, and I've been involved in the IPCC, so it's interesting to compare the views. To my mind, there seems to be a mixed message. On the one hand, you're saying it's possibly too late to avoid disaster. On the other hand, it's worth doing something to reduce emissions to slow the rate of change. So my question really is, if you had the opportunity to speak to the delegations to the Conference of the Parties to the Climate Convention, which meets in December in a few months' time, what would that message be? Because on the one hand, they need encouragement to do something because there's plenty action there to resist doing anything, and I'd be interested to know what your view would be on that. Thank you.
Thank you so much for that really constructive question. If I were asked to address that convention at the end of the year, I would say without hesitation that the most important thing we should all be doing now is to prepare to adapt to the changes that are going to happen. We should stop rather futile attempts to offset global heating, such as by trying to use renewable energy, highly subsidized, to do these. I think these are more just gestures that won't really change the issue at all. It's a global problem, not a European one. So, yes, I think adaptation is it, and I would stress again to anybody living in the British Isles, Norway, Sweden, northern countries, that massive immigration is going to be a major problem, and they should start to consider the building of the housing of refugees in proper cities with a proper infrastructure and adequate hospital and school services and things like that. Not the most awful thing that would happen would be monstrous refugee camps accumulating around. This is a kind of real problem that's going to hit people before very long, regardless of the form of climate change. Rising sea levels, of course, are something to be fought against. As you saw, they're rising twice as fast as the IPCC predicted. What's going to happen to London? Is it adequately covered? I mean, the economy of this country would be grievously affected if the City of London and London itself stopped working. So that is the kind of message I would... If I sound uncertain, you said it's a mixed message, I don't know that I'm right. I'm a scientist. I can't be certain about anything. I can only talk about probabilities.
We're going to take two more questions. One is here, Peter Liss, and the lady there putting her hand up. Unless these are very short, I'm afraid you will miss out. But Peter Liss.
Peter Liss, University of East Anglia. Jim, given the parlous state we appear to be in and fast approaching a worse state, and adaptation and mitigation don't seem to be enough to save us, clearly geoengineering does come onto the horizon. But there are lots of schemes that people suggest, and most of us don't know how reliable these are, whether they work at all, whether they have harmful consequences, unforeseen possibly. And so how do we evaluate which ones to pursue in the sense to put money into research to see whether they would work or not? Do you think it's perhaps time for the Royal Society and maybe the Royal Academy of Engineering to set up a panel to give an authoritative but hard-nosed look at the various possibilities?
Chaired by Professor Peter Liss.
Why not?
If you ask me.
Why not?
Sorry.
Indeed. No, I think that's a very good question, Peter. I don't think I'm the right person to ask here, not being a large-scale engineer. But I do stress what I said earlier. I think we should not hesitate to do experiments, which are not all that expensive compared with, for example, the renewable obligation, which is monstrously expensive and probably will achieve very little. So let's do it. Let's try out things. As you probably all know, Richard Branson's offered a huge prize, which would fund an awful lot of research. $25 million, I think it is, for anyone who can come up with what looks like, to a good panel of judges, a feasible scheme. So, in a sense, something's already being done.
Thank you. This lady.
Fiona Weir, you mentioned briefly that the world's population is 6 billion. Do you agree that, to be realistic, that should be more like 3 billion? And if so, how will this be achieved?
I was afraid somebody would ask that question. I would guess, I don't know, because I'm not a large-scale ecologist, that the carrying capacity of the Earth at the moment is probably not much over 1 billion. The 3 billion would be much too generous. We're just on hiding to nothing, expecting to increase population. It just will crash. It's like any biological system that overpopulates and goes beyond its resource limits. So no, 1 billion or less is probably what we face.
That was a quick answer, so we will take this one. This lady here has been really pressing. It's the same question. So we've solved the problem.
What?
It was the same question, which demonstrates how important it was. And,
well, I'm a bit baffled there. Do you want me to say the same thing that I just said? I'm not pulling back.
Well, I'm sorry we are unable, because of the tightness of the schedule, to continue the questions. But from the numbers, it's quite clear that James has stimulated a huge amount of interest. And as he always does, of course, when he speaks. And I think it's a great credit to him and a measure of the impact that he has in delivering his message, that very unusually there hasn't been a single naysayer amongst you in the audience. And bearing in mind the fact that there are some very big vested interests out there who would like James's message not to be heard and not to be taken attention to, that is, again, a singular indication of the importance of the message you're putting across, James. So, on behalf of us all, could we please thank James in the traditional manner? Thank you. offered to give an encore, but I think we'll take him for a drink instead. Thank you.